The ground beneath your feet feels permanent. Rock seems like the most stable thing in existence. Mountains rise slowly, continents drift almost invisibly, and the planet itself appears calm and finished. But the Earth was not built in calm conditions. Every stone, every grain of sand, every mountain and ocean basin is the leftover material from one of the most violent construction projects in cosmic history. Our planet was assembled through collisions so immense they melted entire worlds, through chaos that lasted tens of millions of years, inside a young solar system where planets did not yet exist, only dust, fire, and gravity slowly learning how to build them. And once we begin tracing that history backward, something remarkable becomes clear. The rocky planets, Mercury, Venus, Earth, and Mars, were not simply formed around the Sun. They were survivors. If you enjoy calm explorations of the universe like this, consider subscribing. And now, let's begin close to home. Stand anywhere on Earth and look down. Beneath your feet is solid rock, perhaps granite, basalt, limestone, or sandstone. It may feel ancient and unchanging, and in human terms it almost is. Some of the oldest rocks on Earth formed more than 4 billion years ago. But even those ancient rocks are younger than the process that created the planet itself. Earth is about 4.5 billion years old. To place that number into perspective, imagine compressing the entire history of our planet into a single calendar year. On that scale, humans appear only in the final few minutes before midnight on December 31st. Written history occupies only the last seconds. Everything else, the formation of the planet, the oceans, the continents, the rise and fall of entire ecosystems, fills the rest of the year. Yet even that enormous stretch of time begins after the most dramatic phase of Earth's creation had already occurred. Because before Earth became a planet, it was something far less impressive. It was dust. To understand how rocky planets were born, we have to step back to a time when the Sun itself had not fully formed. The story begins inside a vast cloud of gas and dust drifting quietly through the Milky Way. These clouds are enormous, sometimes dozens of light years across. They are cold, dark regions where atoms and microscopic grains float in near-perfect stillness. For millions of years, nothing seems to happen. Then gravity begins to pull. A slight imbalance inside the cloud causes material to drift inward. Slowly, almost imperceptibly at first, the cloud begins collapsing toward its center. As it shrinks, gravity squeezes the gas tighter and tighter. The center becomes denser, hotter, brighter. Eventually, that central region becomes what we now call the Sun. But the collapse does not send everything straight inward. The original cloud had a faint spin, almost like a slow whirlpool. As the cloud shrinks, that spin speeds up. The same thing happens when a figure skater pulls their arms inward during a spin. Rotation accelerates. And so the collapsing cloud flattens. Instead of a sphere, it becomes a vast rotating disk of gas and dust surrounding the newborn Sun. Astronomers call this a protoplanetary disk. If we could travel back 4.6 billion years and observe it from a distance, the early solar system would not look like a collection of planets orbiting neatly around a star. It would look more like a glowing whirlpool, an immense pancake-shaped disk of swirling material stretching billions of kilometers outward. The Sun would burn brightly at the center, still young and unstable, blasting radiation and solar wind into the surrounding disk. Inside that disk floated the raw ingredients of every planet that would ever exist here. Tiny particles of dust. These grains were unbelievably small, often no larger than smoke particles. They were made of minerals containing silicon, oxygen, iron, magnesium, and other elements forged long ago in ancient stars. Every rock on Earth, every mountain, every asteroid in the solar system once existed in this disk as microscopic dust. And here is where the first quiet step toward building planets begins. Dust sticks. At first that sounds almost trivial, but in the environment of the young solar system, it was the critical first step toward building worlds. Inside the disk, dust grains constantly drifted and collided with one another. These collisions were gentle, more like drifting snowflakes touching than rocks smashing together. When two grains met, tiny electrical forces between their surfaces allowed them to cling together. Clusters began to form. At first the clumps were fragile, almost like bits of lint. But as they continued colliding with other grains, they slowly grew larger. Millimeter-sized particles became centimeter-sized pebbles. Pebbles became small aggregates. And this process was happening everywhere throughout the disk. Imagine a construction site stretching billions of kilometers across, where every particle of dust is slowly gathering with its neighbors. Over time, the disk begins to change texture. It is no longer just gas and fine dust. It now contains trillions upon trillions of drifting pebbles. At this stage, the process still feels peaceful. Nothing dramatic appears to be happening yet. The disk is simply becoming thicker with these small clumps. But this quiet phase contains the seed of something much more powerful. Because once particles grow large enough, gravity begins to matter. A single pebble has almost no gravitational pull, but when enough material gathers together, even a small object begins to attract nearby particles. And that is when growth accelerates. Imagine rolling a snowball across fresh snow. As it moves, it collects more snow and becomes larger, which allows it to collect even more with each pass. In the early solar system, something similar began to happen. As clusters of rock grew to the size of boulders and then mountains, their gravity started pulling nearby pebbles inward. Material drifted toward them instead of floating past. These growing bodies swept up surrounding particles with increasing efficiency. Within a surprisingly short time, perhaps a few 100,000 years, some objects inside the disk had grown to several kilometers across. They were no longer dust. They were the first solid building blocks of planets. Astronomers call them planetesimals. If you stood on one, it would resemble a small asteroid or a rugged mountain-sized world drifting through space. Some were only a few kilometers across. Others may have reached hundreds of kilometers. And they were everywhere. The inner solar system now contained millions of these rocky bodies orbiting the Sun in slightly different paths. At first they simply passed one another quietly. But gravity does not allow crowded systems to remain peaceful for long. Once planetesimals existed, their mutual attraction began reshaping the entire region. Their orbits tugged on one another. Some drifted closer together, others were nudged into crossing paths. The calm disk of dust was slowly becoming something else. A swarm. And in that swarm, the next stage of planetary construction was about to begin. Because when objects this large collide, they do not simply stick together like dust. They reshape each other. Sometimes they shatter. Sometimes they merge. Sometimes entire worlds are melted in the impact. And over millions of years, this chaotic process will gradually transform a disk filled with countless rocky bodies into only a handful of planets. But before we reach that stage, something else must happen first. Some of those planetesimals are about to grow much larger, large enough that we would recognize them as unfinished worlds. Those early planetesimals were only the beginning. For a short time, the inner solar system contained an astonishing number of them. Millions of rocky bodies drifting around the young sun like a vast swarm of slow-moving debris. Each one followed its own orbit, tilted slightly differently, moving at tens of kilometers per second through a disk still filled with drifting gas and pebbles. At first, most encounters between these bodies were distant passes. Their gravity tugged gently as they moved by one another, altering their paths by tiny amounts. But the more objects existed, the more often those paths crossed. And when they crossed, collisions became unavoidable. Some impacts were destructive. Two bodies might meet at such high speed that they shattered into fragments, creating clouds of debris that spread back into the disk. But many collisions had a different outcome. If the speeds were moderate and the angles favorable, two planetesimals would merge. Their rocks would crush together, their material mixing into a larger object. Each successful collision produced a body with more mass, and that extra mass strengthened its gravity, which meant it could attract even more material. This stage of growth is often described as runaway accretion. The name sounds dramatic, but the underlying idea is simple. Once an object becomes slightly larger than its neighbors, gravity allows it to grow faster than everything around it. The large bodies become larger still. The small ones struggle to keep up. You can imagine it like a crowded highway where one vehicle suddenly begins collecting more and more traffic behind it. As the cluster grows, it pulls in even more vehicles simply because it has become the dominant presence in its lane. In the early solar system, gravity played that role. A few fortunate planetesimals began sweeping up material much more efficiently than the rest. They captured pebbles drifting through the disk, absorbed smaller objects that wandered too close, and gradually expanded. Within a few million years, something extraordinary began to appear inside the disk. Worlds that were no longer small. Some bodies had grown to hundreds of kilometers across, others approached the size of our moon, and eventually a handful reached the scale of Mars. Astronomers call these growing bodies planetary embryos. The name is appropriate. These were unfinished planets, massive spheres of rock and metal still surrounded by swarms of smaller debris, still colliding and absorbing material as they orbited the Sun. If you could witness the inner solar system at this stage, it would look nothing like the quiet planetary system we know today. Instead of 4 stable rocky worlds, you would see perhaps dozens of these embryos circling the Sun in overlapping orbits. Some would be nearly the size of Mars, others would be somewhat smaller. Between them would drift countless leftover planetesimals, fragments of earlier collisions, and streams of rocky debris. And every one of these bodies was gravitationally interacting with the others. This is where the calm construction phase ended. Once planetary embryos formed, the inner solar system entered a period that planetary scientists sometimes describe, half-jokingly, as cosmic demolition derby. Embryos pulled on one another's orbits. Some moved inward toward the Sun, others were pushed outward. Their paths crossed more frequently. Close encounters became common. And eventually worlds began colliding. These collisions were not quick explosions like those we see in movies. On cosmic scales they unfolded slowly, but the energies involved were staggering. 2 Mars-sized bodies approaching each other might collide at several kilometers per second. At that speed, the impact energy could melt enormous volumes of rock. Entire regions of both bodies could vaporize into expanding clouds of superheated material. Yet gravity still dominated the aftermath. The fragments from the collision often fell back together, merging into a single larger world. Each impact reshaped the growing planets. Surfaces melted. Rock oceans formed. Heavy metals began to sink toward the center. This process is known as planetary differentiation. Early planetesimals were essentially mixtures of rock and metal scattered together. But once a body grew large enough and hot enough, gravity began sorting its ingredients. Iron and nickel, dense metals, migrated downward toward the center. Lighter silicate rocks floated upward, forming the outer layers. Imagine molten metal settling at the bottom of a furnace while lighter slag floats above it. The same principle applied on planetary scales. Inside these young worlds, iron slowly gathered into enormous central cores. The result was a layered planet, a metallic core deep inside, surrounded by thick shells of rock. Earth still has that structure today. At the center of our planet lies a core of iron and nickel roughly the size of the moon. Around it sits the mantle, a vast ocean of slowly flowing rock hundreds of kilometers thick. Above that rest the thin crust where continents, oceans, and life eventually appeared. But during the era of planetary embryos, these structures were still forming, and the heat driving this differentiation came from multiple sources. Collisions delivered enormous energy. Radioactive elements inside the rocks released additional heat as they decayed, and the sheer pressure of gravity compressing the interior added more warmth. Many of these early worlds were not solid at all. They were oceans of molten rock. Picture a glowing sphere hundreds or thousands of kilometers wide, its surface a churning sea of magma, drifting through space while smaller bodies rained down upon it. That was the environment in which the inner planets were assembled. And this phase did not last for a few centuries or even a few thousand years. It continued for tens of millions of years. To appreciate that timescale, imagine a human life lasting 80 years. Now imagine that life repeating again and again, over 500,000 times. Only then do we approach the duration of the giant impact phase. Throughout that time, embryos continued colliding, merging, and reshaping each other. Some bodies grew larger with each encounter. Others were shattered and scattered. Some were flung entirely out of the inner solar system by gravitational encounters with their larger neighbors. Gradually, the swarm of embryos began thinning. Each collision reduced the number of major bodies orbiting the Sun. 2 worlds merged into one. Fragments either fell into larger planets or were thrown into distant orbits. Over time, the region that had once contained dozens of competing worlds began narrowing toward a smaller number of survivors. But before that final configuration emerged, one collision would change the history of Earth forever. Roughly 4.5 billion years ago, the young Earth was still growing. It had already reached a size comparable to today's planet, but it remained a molten world surrounded by debris. Somewhere nearby orbited another embryo, likely about the size of Mars. Planetary scientists often call this body Theia. For millions of years, Theia and Earth followed neighbouring orbits around the Sun. Gravitational interactions slowly altered their paths. Eventually, those paths intersected. The collision that followed was not a glancing tap. It was a planetary-scale catastrophe. Theia struck the young Earth at an angle, perhaps moving 10 kilometers per second. The impact released an amount of energy far beyond anything humanity has ever witnessed. Entire sections of both bodies were vaporized. Molten rock blasted outward into space. Yet gravity again shaped the aftermath. Much of the debris did not escape entirely. Instead, it formed a glowing disk of molten rock and vapor orbiting Earth. Over time, that debris began gathering together. Fragments collided and merged, just as planetesimals had done earlier in the disk around the Sun. Within a few thousand years, the debris assembled into a new world. Our Moon. Today the Moon orbits quietly above us, its pale light reflecting sunlight onto Earth's nights. But its existence is the direct result of that ancient impact. A reminder that even planets the size of Earth were still colliding during the final stages of their formation. And Earth itself was transformed. The collision melted large portions of the planet again, creating another global ocean of magma. Over time, the surface cooled, solidified, and formed the earliest crust. But the era of giant impacts had not yet completely ended. Elsewhere in the inner solar system, other embryos were still colliding, merging, or being scattered away. And something else, far larger than any rocky planet, was beginning to influence the entire region. Far beyond the orbit where Earth was forming, a giant world was taking shape. A world whose gravity would soon begin reshaping the destiny of the inner solar system itself. Far from the blazing heat of the inner solar system, beyond the region where rock and metal dominated, the environment around the young Sun was very different. Temperatures dropped with distance. Farther from the Sun, the disk cooled enough that substances which would instantly vaporize near Earth could exist as solid ice. Water froze, carbon dioxide froze, ammonia and methane froze. Suddenly, the amount of solid material available to build planets increased dramatically. In the inner solar system, only rock and metal could condense from the hot disk. But beyond a certain distance, what astronomers call the frost line, ice joined the mix, and ice is abundant. The result was a region rich with building material. Planetesimals formed there too, just as they had closer to the Sun. Dust clumped into pebbles, pebbles into larger bodies, and gravity began pulling everything together. But the extra mass available in this colder region allowed something new to happen. Some growing worlds became enormous. One of them would eventually become Jupiter. At first, Jupiter was likely just another planetary embryo, perhaps several times the mass of Earth, made mostly of rock and ice, but once it reached a certain size, its gravity began capturing enormous amounts of the hydrogen and helium gas surrounding it in the disk. Those gases made up the vast majority of the disk's material. Suddenly, Jupiter's growth accelerated dramatically. Within a relatively short time, perhaps only a few million years, it transformed from a large rocky core into a colossal gas giant more than 300 times the mass of Earth. And once Jupiter reached that size, it began influencing everything around it. Gravity on that scale reshapes entire planetary systems. To appreciate the difference, imagine Earth and Jupiter side by side. Earth's gravity is strong enough to hold our oceans and atmosphere, but Jupiter is so massive that more than 1,000 Earths could fit inside its volume. Its gravitational reach extends across enormous distances. As Jupiter grew inside the protoplanetary disk, it began interacting strongly with the gas around it. The giant planet created waves in the surrounding material, carving partial gaps into the disk as it orbited the Sun. And these interactions had consequences. Instead of remaining in a fixed orbit, Jupiter may have begun to migrate. Planetary migration is one of the great surprises of modern astronomy. For centuries, people assumed planets formed roughly where we see them today. But computer simulations and observations of young star systems tell a different story. Planets can move. When a massive planet like Jupiter interacts gravitationally with the gas disk around it, angular momentum can shift. The planet may slowly drift inward toward the star. This idea forms the heart of a leading model known as the Grand Tack. According to this scenario, Jupiter did not stay in its present orbit during the early solar system. Instead, it likely moved inward toward the Sun before reversing direction and migrating outward again. The motion is sometimes compared to a sailing maneuver called a tack, where a boat turns sharply while navigating against the wind. In this cosmic version, Jupiter first drifted inward, perhaps approaching as close as the modern orbit of Mars. And then something remarkable happened. Another giant planet was forming behind it. Saturn. As Saturn grew and moved inward as well, the gravitational interactions between the two giants changed their motion. Instead of continuing their inward migration, both planets began moving outward together. They effectively reversed course. But during the time Jupiter spent moving inward, it passed directly through the region where many of the rocky embryos and planetesimals were orbiting. And Jupiter's gravity did not treat them gently. Imagine a massive bulldozer rolling slowly through a crowded construction site filled with unfinished structures. Objects are pushed aside, scattered, broken apart, or thrown far away. Jupiter played a similar role in the young solar system. As it migrated inward, its immense gravity destabilized many of the orbits in the inner disk. Some planetesimals were flung outward toward the asteroid belt. Others were scattered inward toward the Sun. Entire regions of the disk were partially cleared. Material that might otherwise have assembled into additional planets was disrupted or removed. Then, when Jupiter reversed course and moved outward again, it stirred the region a second time. The combined effect of this gravitational upheaval was profound. Instead of forming many large rocky planets in the inner solar system, the available material became limited. And that helps explain something curious about our planetary neighbourhood. If you look at the 4 rocky planets today, their sizes are not evenly distributed. Earth and Venus are large, almost twins in mass and diameter. Mercury is much smaller. And Mars is surprisingly tiny compared to Earth. In fact, Mars is only about 1/10 the mass of our planet. For many years, this imbalance puzzled planetary scientists. Computer simulations that tried to build the inner solar system often produced a Mars that was far too large. But if Jupiter passed through the region early in solar system history, it would have removed a great deal of material that Mars might otherwise have gathered. In that case, Mars becomes what scientists sometimes call a stranded planetary embryo, a world that began forming like the others, but ran out of building material before it could grow larger. Mercury may carry its own scars from the violent early era as well. Compared to other rocky planets, Mercury has an unusually large iron core. The metal interior occupies a huge fraction of the planet's total size. One possible explanation is that Mercury originally formed larger, with a thicker mantle of rock surrounding its core. Later, a massive collision may have stripped away much of that outer rock, leaving behind the dense metal-rich world we see today. The solar system preserves these histories quietly. Each rocky planet is like a survivor carrying the marks of the process that created it. Venus grew to nearly the same mass as Earth, but followed a different evolutionary path afterward, developing a dense carbon dioxide atmosphere and a surface hot enough to melt lead. Mars remained small, cooling quickly and losing most of its atmosphere early in its history. Mercury endured extreme impacts close to the Sun, and Earth continued evolving through a long series of collisions and cooling phases that eventually allowed oceans, continents, and life. But during the earliest tens of millions of years, none of these worlds were stable. The giant impact phase was still underway. Planetary embryos continued crossing paths. Some collisions were catastrophic, others merged bodies into larger planets. The number of worlds orbiting the Sun kept decreasing. 2 embryos collided and became one. Fragments were swept up by larger planets. Occasionally a body was hurled completely out of the inner solar system, becoming a wandering object lost to interstellar space. Gradually the chaos subsided. With each collision the number of major bodies dropped, and with fewer large objects remaining, the frequency of impact slowly declined. The inner solar system was beginning to settle. By roughly 100 million years after the Sun's birth, the basic architecture we recognize today had largely emerged. 4 primary rocky planets remained: Mercury, Venus, Earth, Mars, each one occupying its own stable orbit around the Sun. But beneath that calm arrangement lay the record of everything that had happened before. every crater on Mercury, every ancient lava plain on the Moon, every meteorite that falls to Earth. They are fragments of that earlier era, relics of a time when planets were not yet finished worlds, but molten bodies colliding again and again inside a young solar system, still deciding what it would become. And even today, scattered throughout space, small pieces of that ancient construction site continue to drift. Asteroids, leftover building blocks that never fully joined a planet. Some of those leftover fragments still reach us. Every year, thousands of small pieces of space rock plunge into Earth's atmosphere. Most burn up as brief streaks of light, meteors flashing across the night sky. Occasionally a larger fragment survives the fiery descent and lands on the surface. When that happens, we call it a meteorite. To most people, a meteorite is simply a strange rock from space, but to planetary scientists, meteorites are something far more valuable. They are fossils from the birth of the solar system. Many meteorites formed before the planets finished assembling. Some solidified inside planetesimals that existed during the earliest few million years after the Sun formed. Others are fragments blasted from larger bodies during later collisions. When scientists study these rocks in laboratories, they often discover something remarkable. Many meteorites are older than any rock found on Earth. Their ages cluster around 4.56 billion years. That number is not random. It marks the approximate moment when solid material first condensed from the solar nebula, the disk of gas and dust surrounding the newborn sun. In other words, some meteorites preserve the very first solid grains that would eventually become planets. Inside them, we sometimes find tiny spherical droplets called chondrules. These formed when dust particles were briefly melted and then cooled rapidly inside the early disk. Their presence tells us that the environment around the young sun was dynamic, filled with heating events and shock waves that briefly liquefied small particles before they solidified again. Other meteorites contain even more ancient material. Embedded within them are microscopic mineral grains that formed long before the sun existed. These grains were created in distant stars that died and expelled their material into space billions of years ago. Those ancient atoms drifted through interstellar clouds, eventually becoming part of the gas and dust that collapsed to form our solar system. So when a meteorite lands on Earth, it sometimes carries material older than our star. That alone is enough to reshape how we think about the ground beneath our feet. Because the atoms in the rocks around us have lived many lives. Some were forged inside exploding stars long before the sun was born. Later they drifted through space, gathered into the solar nebula, clumped into dust grains, merged into planetesimals, collided inside growing worlds, melted, separated into cores and mantles, and finally cooled into the rocks we know today. The Earth itself is a collection of these ancient fragments. Yet for a long time, the early history of the solar system remained mysterious. We knew the planets existed, and we knew roughly how old they were, but the details of how dust became worlds were uncertain. Over the past few decades, that picture has begun to sharpen dramatically. One reason is that astronomers can now observe other planetary systems forming around distant stars. Young stars often appear surrounded by glowing disks of gas and dust, structures remarkably similar to the solar nebula that once encircled our own sun. Telescopes sensitive to infrared and radio wavelengths can peer into these disks, revealing rings, gaps, and swirling patterns where planets may already be forming. Some disks show dark lanes carved into the surrounding material, likely produced by growing planets clearing their orbits. In other systems, we observe massive planets orbiting extremely close to their stars, evidence that planetary migration is common. These observations confirm something profound. Planet formation is not unique to our solar system. It appears to be a natural outcome of star formation itself. Wherever a young star forms inside a collapsing cloud of gas and dust, a rotating disk usually forms around it, and within that disk, the same fundamental processes begin unfolding. Dust collides and sticks. Pebbles accumulate. Planetesimals form. Gravity gathers them into embryos. Embryos collide and merge into planets. The details vary. Some systems produce giant planets close to their stars. Others create chains of rocky worlds packed tightly together. Some may even lose their planets entirely through gravitational chaos. But the underlying process is remarkably universal. And that realization changes how we see the rocky planets in our own solar system. For most of human history, Earth seemed like a unique place, perhaps even the only solid world in existence. But now we know that rocky planets are common throughout the galaxy. Thousands of them have already been discovered orbiting distant stars. Some are larger than Earth, some are smaller. Many exist in systems very different from our own. Yet the physics that built them is the same. Gravity pulling matter together, collisions reshaping growing worlds, heat melting rock and separating metal from stone. Over millions of years, these processes gradually transform a chaotic disk of debris into stable planets. Still, even though rocky planets are common, their exact properties can vary enormously. And that variation becomes especially clear when we look closely at the 4 telluric worlds of our own inner solar system. At first glance, they seem similar. All 4, Mercury, Venus, Earth, and Mars, are made primarily of rock and metal. None possess the thick hydrogen atmospheres that dominate the gas giants. Their sizes fall within a relatively narrow range compared to the vast planets farther out. Yet when we examine them more carefully, the differences are striking. Mercury is scorched and airless, its surface battered by craters and extreme temperature swings. One side may reach hundreds of degrees above boiling water, while the night side plunges into deep cold. Venus, almost identical to Earth in size, is wrapped in an atmosphere so dense and hot that its surface pressure is more than 90 times that of Earth's. Thick clouds of sulfuric acid swirl above a landscape hot enough to melt lead. Earth is the only world known to host liquid oceans and life. Mars is smaller and colder, its atmosphere thin, its rivers long since dried, its surface preserving the scars of ancient water and volcanic activity. These 4 planets formed from the same disk of material around the same star, during the same general period of cosmic history, yet they ended up radically different. To understand why, we have to look deeper into how planets cool, how atmospheres evolve, and how delicate the balance can be between a world that becomes stable and one that becomes hostile. Because the story of planetary formation does not end when the collisions stop. That moment, when the final giant impacts fade and the orbits stabilize, is only the beginning of another long chapter. The chapter in which molten worlds slowly cool, crusts solidify, atmospheres develop, and surfaces begin to change. During those early millions of years, the Earth was still far from the blue planet we recognize today. Its surface glowed with heat. The air above it was thick with volcanic gases. Asteroids and comets still occasionally struck the planet, delivering additional material from the outer solar system. But gradually, the chaos of the giant impact phase faded. The inner solar system began to quiet, and the planets that had survived the violent assembly process were about to begin shaping their own individual destinies, each one carrying the scars of its birth, each one following a slightly different path through the same cosmic story. Because in the end, the formation of the inner solar system was not a neat construction project. It was a long competition, a slow elimination process in which countless bodies formed, collided, merged, shattered, and disappeared. And the 4 rocky planets we see today are simply the final few left standing. Once the era of giant impacts began fading, the inner solar system started to look less like a battlefield and more like a planetary system. Not calm yet, but calmer. The largest surviving bodies, Mercury, Venus, Earth, and Mars, now dominated their own regions of space. Each planet's gravity had cleared much of the nearby debris, either sweeping it up through impacts or flinging it into distant orbits. Yet the planets themselves were still very different from the worlds we see today. They were hot. Extremely hot. Many of them had spent tens of millions of years absorbing the energy of collisions, compressing under their own gravity, and accumulating radioactive elements whose decay released additional heat. The result was that young rocky planets often began their lives covered by magma oceans, vast seas of molten rock stretching across their surfaces. Imagine standing above Earth at that time. Instead of blue oceans and white clouds, the entire planet would glow with a dim red light. Rivers of molten rock would slowly circulate across the surface, while enormous volcanic plumes erupted into the thick atmosphere above. The sky itself would look different too. The moon, freshly formed from the debris of the giant impact, orbited far closer than it does today. It may have appeared several times larger in the sky, rising and setting rapidly as Earth spun faster than it does now. The atmosphere would have been heavy with volcanic gases, water vapor, carbon dioxide, nitrogen, sulfur compounds released from the molten interior. For a long time, liquid water could not exist on the surface. Any water delivered by asteroids or trapped inside the rocks would instantly boil into steam in that intense heat. But planets cool. Even objects the size of Earth eventually lose heat into space. Radiation carries energy away, and over time the molten surface begins to solidify. The first crust forms. On Earth, this process may have taken tens of millions of years. The earliest solid crust likely formed as patches of cooling rock floating atop the magma ocean, somewhat like thin ice forming on a freezing lake. These patches thickened and expanded as cooling continued. Eventually, solid rock covered most of the surface. Once that happened, a new phase of planetary evolution could begin. Volcanic gases released from the interior accumulated in the atmosphere. As temperatures slowly dropped, water vapor in the air began condensing into liquid. Rain fell. Not gentle showers like we know today, but immense storms lasting thousands of years. Water condensed from the atmosphere and poured onto the hot surface, gradually filling the lowest basins. The first oceans were born. These oceans may have appeared surprisingly early in Earth's history, perhaps within a few 100 million years after the planet formed. Evidence comes from tiny mineral crystals called zircons found in ancient rocks in Australia. Some of these crystals formed around 4.4 billion years ago and appear to have crystallized in the presence of liquid water. That means Earth may have had oceans not long after the giant impact that created the Moon. Meanwhile, the interior of the planet continued evolving. Remember the differentiation process that began during the early collisions. Heavy metals had sunk toward the center, while lighter rock floated above. Inside Earth, that process created a massive iron core surrounded by a thick mantle of silicate rock. But the mantle was not completely solid. Even today, the rock deep within Earth flows slowly over millions of years, circulating heat outward from the interior. This slow motion drives plate tectonics, the movement of continents and ocean basins across the planet's surface. In the early Earth, this internal heat was even stronger. The young planet churned from within. Volcanoes erupted frequently. New crust formed and was recycled. Chemical elements moved between the interior, the atmosphere, and the oceans. This constant reshaping would eventually help create conditions suitable for life. But before we return fully to Earth, it's worth stepping back to consider something subtle about the inner solar system. The rocky planets formed only within a narrow region around the Sun. Closer than that region, temperatures were too high for solid rock to remain stable during the earlier stages of the disk. Farther out, ice and gas dominated, allowing giant planets to grow instead. The inner solar system became a kind of cosmic foundry. In that zone, temperatures allowed minerals containing silicon, oxygen, iron, and magnesium to condense into solid grains, while lighter volatile substances remained gaseous. The result was that the building blocks of the inner planets were dense and rocky. Iron and nickel formed metallic cores. Silicate minerals formed mantles and crusts. By contrast, the outer solar system contained huge amounts of frozen water, methane, and ammonia, along with thick envelopes of hydrogen and helium gas. This chemical sorting explains why the planets closest to the Sun are relatively small and rocky, while the outer planets are enormous gas and ice giants. It also explains why rocky planets tend to have solid surfaces. The materials that formed them were heavy enough to settle and compact under gravity. But even within this rocky zone, small differences in distance from the Sun created important consequences. Mercury, the closest planet, formed in an environment far hotter than the one where Earth formed. That heat influenced which materials could condense and how the planet evolved. Mercury ended up dense and metal-rich, with little atmosphere and extreme temperature variations. Mars formed farther out, where the disk was cooler but also less dense. There simply was not as much material available in that region once Jupiter's migration had disrupted the disk. As a result, Mars grew slowly and remained relatively small. Because of its small size, Mars cooled faster than Earth. Its internal heat faded earlier. Volcanic activity declined, its magnetic field weakened, and over time much of its atmosphere escaped into space. Earth and Venus, by contrast, formed in a region where more building material remained. Both grew to similar sizes, giving them enough gravity to retain thick atmospheres and enough internal heat to remain geologically active for billions of years. Yet even these two near-twin planets diverged dramatically. Earth developed stable oceans and a climate that allowed life to flourish. Venus evolved into a world trapped beneath an immense greenhouse atmosphere, where surface temperatures now exceed 460 degrees Celsius. That divergence reminds us of something important. The process that builds planets is chaotic and sensitive to small differences. Two worlds may begin with similar sizes and compositions, yet end up radically different depending on how their atmospheres evolve, how their interiors cool, and how sunlight interacts with their surfaces. But long before those later differences emerged, all four rocky planets shared the same beginning. They were assembled from dust. Tiny grains drifting inside a disk around a newborn star. Grains that stuck together. Pebbles that gathered into rocks. Rocks that grew into mountains drifting through space. Mountains that merged into worlds. And worlds that collided until only a few survivors remained. The calm arrangement of planets we see today hides that violent past remarkably well. When we look up at the night sky, the solar system appears orderly. The planets follow predictable paths. Their orbits remain stable for millions of years. But stability came only after an immense sorting process. Countless early worlds were destroyed. Some merged into larger planets. Others were scattered outward to become asteroids. Some may have been thrown entirely out of the solar system, wandering the galaxy as lonely rogue planets. The four rocky planets we see today are simply the final configuration that remained once the chaos settled. And the evidence of that ancient chaos is still visible if we know where to look. On the Moon, enormous circular basins mark the scars of colossal impacts from the earliest era. Mercury's surface is covered in craters from countless collisions. Mars preserves ancient volcanic plains and dried river valleys. Even Earth, though its active geology constantly reshapes the surface, still carries hints of those distant events buried deep within its oldest rocks. All of it traces back to the same beginning, a quiet disk of dust surrounding a young sun, a disk that slowly learned how to build worlds. That quiet disk did not look like a place where worlds were being assembled. If we could drift through it during the first few million years after the sun formed, the scene would appear strangely empty. The gas was thin, far thinner than any atmosphere on Earth. Dust floated in faint clouds, barely visible except where sunlight scattered off the tiny particles. There were no continents, no mountains, no recognizable planets, only countless grains drifting through an enormous rotating disk. And yet hidden inside that quiet environment was the machinery that would eventually build entire worlds. The key ingredient was patience. On human timescales, almost nothing seemed to happen. Dust drifted, collided gently, and sometimes stuck together. Pebbles moved slowly through the gas, spiraling inward toward the sun under the influence of subtle drag forces. But over thousands of years, then millions, these tiny interactions accumulated. The disk slowly evolved. Regions with slightly higher concentrations of material became gravitationally unstable. Streams of pebbles gathered together, forming dense swarms. In some areas, these swarms collapsed suddenly under their own gravity. That collapse could happen surprisingly quickly. Instead of building kilometre-sized bodies one pebble at a time, entire clusters of material might suddenly compress into large planetesimals almost at once. Computer simulations suggest that under the right conditions, a cloud of drifting pebbles could collapse into a rocky body tens or even hundreds of kilometres across. A mountain-sized object born in a single gravitational moment. This mechanism helps explain something puzzling that scientists once struggled with. If planetesimals formed only through slow, step-by-step collisions of pebbles, the process might stall before reaching large sizes. Pebbles tend to bounce or fragment when they collide too quickly. But if dense streams of pebbles collapse gravitationally, the system can leap forward. Suddenly the disk contains large objects capable of dominating their surroundings. Once those bodies exist, gravity takes control of the story. And gravity is relentless. Every object with mass pulls on every other object. The larger something becomes, the stronger its influence grows. Over time, even subtle gravitational tugs reshape orbits and bring bodies closer together. At first the interactions were gentle. Planetesimals passed one another like slow ships crossing a quiet sea. But as their numbers increased and their sizes grew, the encounters became more dramatic. Small shifts in orbit could place two bodies on intersecting paths. Once that happened, the collision might take millions of years to occur. But eventually it would, and when it did, the impact reshaped both participants. It helps to imagine these encounters not as explosive moments, but as slow cosmic events unfolding across immense distances. Two bodies approaching one another from thousands of kilometers apart would feel each other's gravity long before the impact. Their paths curved inward. Their relative speed increased. And then, at the moment of collision, their surfaces met with enormous energy. The rock at the point of contact might instantly melt or vaporize. Shock waves rippled through the interiors of both bodies. Fragments blasted outward. Yet gravity again gathered the debris. Much of the shattered material fell back together, forming a larger combined body. Each collision was both destruction and creation. Broken worlds became bigger worlds. Over time, this repeated process changed the balance of the entire disk. The number of large bodies decreased, but the surviving ones became more massive. And the larger they grew, the more powerful their gravitational reach became. This phase of planetary growth created a hierarchy. A few dominant embryos controlled their regions of space. Smaller planetesimals were either absorbed by these growing worlds or scattered into new orbits. Gradually, the embryos carved out feeding zones, orbital neighborhoods where their gravity determined the fate of nearby material. If a smaller object wandered into that zone, it was likely to collide with the embryo sooner or later. In this way, the embryos continued to grow. But their growth was not unlimited. As each embryo cleared its neighborhood, the amount of available material declined. Eventually, most nearby debris had either been captured or scattered away. The embryos reached a stage where further growth required collisions with other embryos. And that is when the solar system became truly violent. Imagine a region of space containing perhaps 20 Mars-sized worlds orbiting the Sun at different distances. Each one is gravitationally tugging on the others. Their orbits are not perfectly circular. They wobble slightly. Over thousands of orbits, those small variations accumulate. Two embryos drift closer. Their gravitational pull alters each other's path. The encounter changes their orbital shapes just enough that on a future pass, their paths intersect. And then the collision occurs. These events were rare on human timescales, but inevitable across millions of years. When two planetary embryos collided, the outcome depended on their speed and the angle of impact. A direct collision could merge the two bodies into one larger planet. A glancing blow might strip material from one world and scatter debris across the region. In some cases, both worlds were partially shattered, with fragments eventually reassembling into new combinations. The giant impact that formed the Moon was one of these encounters, but it was not unique. Many similar events occurred during the early solar system. Some embryos were completely destroyed. Others grew dramatically. And with each major collision, the number of large worlds orbiting the Sun continued to shrink. Picture a crowded field slowly emptying. At the beginning, dozens of unfinished planets competed for space. Then 20. Then 10. Then only a few remained. Each survivor carried the material of many earlier bodies within it. In a sense, Earth is not just one world. It is the combined remains of many worlds that existed before it. Inside our planet's mantle and core lie the remnants of countless planetesimals and embryos that merged together during that chaotic era. The atoms in your bones were once part of those ancient bodies. That realization adds a strange intimacy to planetary formation. The rocks beneath our feet are not merely old. They are composites, fragments of multiple early worlds fused together through collision and gravity. And while the giant impact phase gradually reduced the number of competing embryos, the solar system was still evolving in other ways as well. The gas disk that surrounded the young sun was slowly dissipating. Radiation from the star pushed gas outward. Stellar winds blew material away into space. Over a few million years, the once thick disk became thinner and thinner. Eventually, most of the gas disappeared entirely. That moment mattered enormously. While the gas remained, it acted like a kind of cosmic cushion. Gas drag dampened orbital motions and slowed the movement of smaller bodies through the disk. Once the gas vanished, the remaining rocky bodies moved through nearly empty space. Without that cushioning effect, gravitational interactions became more chaotic. Orbits stretched and tilted. Encounters between embryos became more energetic. The final stage of planetary assembly intensified. And slowly, through repeated collisions, the architecture of the inner solar system approached the configuration we know today. Mercury close to the Sun, Venus and Earth larger and more massive, Mars smaller and stranded farther out. Between Mars and Jupiter remained a region filled with leftover fragments, the asteroid belt. Those asteroids are survivors too. Some are pieces of planetesimals that were shattered long ago. Others are primitive bodies that never grew large enough to become planets at all. Jupiter's powerful gravity prevented them from merging into a larger world. Instead, they remained scattered through that region, quietly orbiting the Sun as relics of the construction era. Together they preserve a memory of the solar system's earliest days, a time when dust became pebbles, pebbles became mountains, mountains became worlds, and worlds collided until only a few remained to circle the Sun in lasting stability. Even after the largest collisions ended, the inner solar system did not immediately become peaceful. The giant embryos had mostly finished merging into the 4 rocky planets we recognize today, but countless smaller bodies still wandered through space. Asteroids, fragments of shattered worlds, and leftover planetesimals continued drifting across the planetary region. Many of them eventually encountered the young planets. The evidence of this era is written clearly across the surface of the Moon. If you look up at the Moon tonight, its pale face seems calm and timeless, but through a telescope, the surface reveals thousands of circular craters, some small, some stretching hundreds of kilometers across. Those craters are the scars of impacts. Unlike Earth, the Moon has almost no atmosphere and very little geological activity. There are no oceans, no plate tectonics, no erosion strong enough to erase most ancient features. As a result, the Moon preserves a remarkably clear record of the collisions that occurred during the early solar system. When scientists dated rocks brought back by the Apollo missions, they discovered that many large lunar impact basins formed during a relatively short window, roughly 3.9 billion years ago. This period is sometimes called the Late Heavy Bombardment. The name captures the idea that, long after the planets themselves had formed, the inner solar system experienced a surge of impacts from leftover debris. Exactly what triggered that surge remains an active area of research. One possibility involves the slow rearrangement of the giant planets in the outer solar system. As Jupiter, Saturn, Uranus, and Neptune interacted gravitationally with the remaining disk of icy bodies beyond them, their orbits may have shifted slightly. Those changes could have destabilized large populations of asteroids and comets, sending many of them inward toward the rocky planets. If that scenario is correct, the inner solar system may have briefly experienced a rain of impacts lasting tens of millions of years. Earth would have been struck many times during this period as well. But because Earth's surface is constantly reshaped by plate tectonics, erosion, and volcanism, most of those ancient craters have disappeared. Their traces lie buried deep beneath younger rock. The Moon, by contrast, still carries the record openly. From a distance, those basins look like dark circular patches on the lunar surface. Some were created by objects dozens of kilometers across, striking the Moon with enormous force. Each impact released energy far beyond anything produced by human technology. Yet even this violent chapter eventually ended. As time passed, the supply of wandering debris declined. Asteroids either struck planets, were ejected from the solar system, or settled into stable orbits that avoided major collisions. The inner solar system entered a long period of relative calm. Planets now followed predictable paths around the Sun, completing each orbit with remarkable stability. Occasional impacts still occurred, but the frequency dropped dramatically compared with the early chaotic era. That quiet stability allowed something extraordinary to unfold on at least one world. Earth began to transform. With oceans covering much of the surface and volcanic gases forming an atmosphere above, chemical reactions filled the seas with dissolved minerals and complex molecules. Lightning, ultraviolet radiation from the young sun, and heat from volcanic vents all provided energy capable of driving new reactions. Somewhere within that restless environment, molecules began organizing themselves in new ways. At first the steps were small, chains of atoms forming more complex structures, certain chemical systems becoming capable of copying themselves with slight variations. Over immense spans of time, those simple systems evolved into living organisms. The earliest life on Earth may have appeared more than 3.5 billion years ago. That means life began relatively soon after the planet's surface cooled enough for oceans to exist. From there, the story of Earth diverges sharply from the other rocky planets. Because once life emerged, it began reshaping the planet itself. Microorganisms released oxygen into the atmosphere through photosynthesis. Over hundreds of millions of years that oxygen accumulated, transforming the chemistry of the air and oceans. Complex cells evolved. Multicellular life appeared. Eventually plants, animals, forests, and entire ecosystems covered the continents and seas. All of that biological richness emerged on a planet whose origin lay in molten rock and planetary collisions. The connection between those early violent events and the life we see today is not always obvious, but the link is real. The giant impact that formed the Moon may have helped stabilize Earth's rotation and tilt, influencing the long-term stability of our climate. The differentiation that created Earth's iron core also generated the planet's magnetic field, which shields the surface from harmful solar radiation. The early delivery of water and volatile elements by asteroids and comets may have helped supply the ingredients for oceans and atmosphere. Even the slow movement of tectonic plates, driven by heat left over from Earth's formation, continues cycling nutrients through the planet's surface environments. In other words, the same processes that built the planet also created conditions that allowed life to develop. But Earth's path was not inevitable. Small differences during planetary formation could have produced a very different outcome. If Earth had formed slightly closer to the Sun, it might have experienced runaway greenhouse heating like Venus. If it had been much smaller, like Mars, its internal heat might have faded quickly, weakening its magnetic field and allowing its atmosphere to escape. If the giant impact that created the Moon had occurred at a different angle or speed, Earth's rotation or internal structure might have evolved differently. Planetary formation involves a delicate balance between gravity, chemistry, and timing. And that balance does not always produce habitable worlds. When astronomers began discovering planets around other stars in the 1990s, they expected to find systems somewhat similar to our own. Instead, many of the first discoveries were surprising. Some stars host giant planets orbiting extremely close to the star, so close that a year lasts only a few days. Others have massive planets following highly elongated orbits, swinging dramatically toward and away from their stars. In many systems, planetary arrangements appear far more chaotic than the one we see in our solar system. Those discoveries reinforced an important lesson. Planet formation is common, but stable systems like ours, where small rocky planets orbit safely in the inner region, while giant planets remain farther out, may not be the most typical outcome. In some systems, migrating giant planets may sweep through the inner regions, destroying or ejecting rocky worlds before they fully form. In others, multiple giant planets may gravitationally scatter one another into unstable orbits, disrupting the entire system. Yet even within that diversity, the basic ingredients remain the same. Dust, gas, gravity, time. Wherever stars form inside giant molecular clouds, disks of material appear around them. Within those disks, particles begin the slow process of assembling into larger structures. Pebbles form, planetesimals appear, embryos collide, worlds emerge, and somewhere in that vast range of possibilities, rocky planets like Earth are built. Which means the story of our own planet is not just a local history. It is one version of a process happening across the galaxy. Billions of stars are surrounded by their own planetary systems. Around many of them, rocky worlds likely formed through the same chaotic steps that shape the inner solar system. Some of those worlds may still be molten and violent. Others may have cooled long ago, their surfaces quiet and ancient. And on a few of them, perhaps, oceans and atmospheres may have allowed life to appear, just as it did here. All of those distant planets share the same fundamental beginning. A quiet disk of dust around a young star. A disk where tiny grains slowly began the long journey toward becoming worlds. When we imagine planets forming, it is tempting to picture a smooth process. Dust gathers gently, worlds grow steadily. Eventually neat, finished planets settle into stable orbits. Reality is far less tidy. The early inner solar system was more like a crowded arena where gravity constantly rearranged the participants. Even small differences in position or mass could change everything over millions of years. Two embryos might begin in nearly identical orbits. For a long time they circle the sun peacefully, separated by millions of kilometers. But gravity never truly rests. Every orbit slightly alters the next one. Tiny tugs accumulate. The paths stretch, tilt, and drift. Eventually those two worlds begin passing closer to each other. Then one close encounter shifts their trajectories again. The next time they meet, the distance shrinks. After enough of these interactions, their paths cross completely. The collision becomes inevitable. These slow gravitational dances played out across the entire inner solar system during its youth. Each encounter was like a subtle negotiation of space, worlds adjusting to one another until only a few stable arrangements remained possible. That is why the final architecture of a planetary system often looks simple, even though the process that produced it was incredibly chaotic. The calm we see today is the result of long-term elimination. Imagine a crowded room where dozens of people are trying to find comfortable positions without bumping into each other. Over time, individuals move, step aside, or leave until only a few remain spaced comfortably apart. Something similar happened among the planetary embryos. The ones that survived ended up in orbits that rarely cross. Mercury circles closest to the Sun in a tight, fast path. Venus follows farther out. Earth occupies a slightly larger orbit, and Mars drifts beyond it. The distances between them are not random. Those separations represent stable gravitational arrangements that emerged after tens of millions of years of collisions and scattering. Even now, those orbits are not perfectly still. Each planet's gravity continues tugging gently on the others. Over long spans of time, their orbital shapes slowly shift and wobble. But these changes remain small enough that the overall structure of the system stays intact. That stability is precious. Without it, planetary climates could fluctuate wildly as orbits stretched and shifted unpredictably. Worlds might collide again or be flung into deep space. Instead, the inner solar system settled into a long-lived balance. But beneath that calm arrangement lies another subtle consequence of the violent beginning. Every rocky planet carries a layered interior. Earlier we touched on differentiation, the process by which heavy metals sank toward the center, while lighter rock rose above. This separation happened when the planets were still extremely hot, their interiors partially molten. Once differentiation occurred, it permanently shaped how those worlds evolved. At the center of Earth lies an iron core about 3,500 kilometers in radius. The outer portion of that core is liquid metal, slowly churning due to heat escaping from the deep interior. That motion generates Earth's magnetic field. Invisible lines of magnetic force extend outward into space, forming a protective bubble around the planet. This magnetosphere deflects much of the charged particle radiation streaming outward from the Sun. Without it, Earth's atmosphere might have been gradually stripped away over billions of years. Mars offers an example of what can happen when that protection fades. Early in its history, Mars likely possessed a magnetic field similar to Earth's. Evidence from magnetized rocks suggests that its core once generated a global magnetic shield. But because Mars is much smaller than Earth, its interior cooled more quickly. As the planet lost internal heat, the motion inside its core slowed. Eventually the magnetic field weakened and disappeared. Without that protective barrier, the solar wind, a stream of energetic particles flowing from the Sun, began interacting directly with Mars's upper atmosphere. Over millions of years, that interaction stripped away much of the atmosphere into space. Today Mars retains only a thin remnant of its once thicker air. The planet still preserves signs that liquid water once flowed across its surface. Ancient river channels, lake basins, and mineral deposits formed in watery environments. But with most of its atmosphere gone, the surface now remains cold and dry. Earth avoided that fate partly because of its greater size and internal heat, which allowed its magnetic field to persist. Venus presents a different story. Venus is almost the same size as Earth, yet its atmosphere evolved in a dramatically different direction. The planet likely began with water and volcanic gases similar to Earth's early atmosphere. But because Venus orbits closer to the Sun, its surface received more solar energy. That additional heat may have prevented long-term oceans from stabilizing. Without oceans to absorb carbon dioxide through chemical weathering processes, the greenhouse effect intensified. As temperatures rose, more water vapor accumulated in the atmosphere. Water vapor itself is a powerful greenhouse gas, trapping additional heat. The cycle fed on itself. Eventually the surface became hot enough that oceans could not exist at all. Water molecules in the upper atmosphere were broken apart by sunlight, and the hydrogen escaped into space. What remained was a dense carbon dioxide atmosphere that trapped enormous amounts of heat. Today, Venus is the hottest planet in the solar system. Even though Mercury orbits closer to the Sun, Mercury lacks the thick atmosphere needed to trap heat. Venus, wrapped in dense clouds, holds its warmth relentlessly. The surface temperature exceeds 460 degrees Celsius. A world nearly identical in size to Earth became utterly inhospitable. These diverging paths remind us that planetary formation does not end with the creation of solid worlds. Formation sets the stage. What happens afterward? How atmospheres evolve, how interiors cool, how sunlight interacts with each planet, determines what those worlds eventually become. Yet despite all those differences, the four rocky planets share a common ancestry. Each one emerged from the same rotating disk of gas and dust around the young sun. Each one passed through the same stages of growth. Dust to pebbles, pebbles to planetesimals, planetesimals to embryos, embryos to planets through immense collisions. That sequence may sound straightforward when summarized in a few steps, but the reality stretched across tens of millions of years and involved countless individual events. Each collision slightly changed the future. Each gravitational encounter reshaped the system's architecture. Each planet accumulated a unique mixture of materials from across the disk. And even now, long after the main construction phase ended, small remnants of that era continue orbiting quietly between Mars and Jupiter. The asteroid belt. From a distance, it might sound like a dense swarm of rocks, but in truth the asteroids are spread across enormous distances. If you stood on one asteroid and looked around, the nearest neighbour might be millions of kilometres away. Yet collectively they preserve an archive of early solar system history. Some asteroids are primitive, containing material that has barely changed since the solar nebula first condensed. Others are fragments of the larger bodies that once partially melted and differentiated before being shattered by impacts. By studying these objects, through telescopes, spacecraft missions, and meteorites that fall to Earth, scientists can piece together clues about the processes that built the planets. In that sense, the asteroid belt is like a museum of planetary construction. Every rock there holds a small piece of the story. And when we combine those clues with computer simulations, observations of young planetary disks around other stars, and the geological records preserved on planets and moons, the picture becomes clearer. The inner solar system was never designed. It was assembled, slowly, violently, and improbably, from dust drifting around a newborn star. One of the quiet surprises of planetary science is how inefficient the process of building planets actually is. At the beginning, the solar nebula contained an enormous amount of material: gas, dust, ice, and rock spread across a disk billions of kilometers wide. If that material had gathered perfectly, the inner solar system might have produced many large rocky planets. But it didn't. Most of the solid matter never became part of the final worlds. Instead, a great deal of it was lost along the way. Some fell into the sun, some was ejected from the solar system entirely by gravitational encounters, some remained scattered as asteroids and smaller debris. Only a fraction ultimately assembled into Mercury, Venus, Earth, and Mars. In that sense, the rocky planets are not the inevitable outcome of the disk's material. They are the survivors of a long sorting process. Imagine once again that early swarm of planetesimals and embryos orbiting the young sun. The region inside what would become the orbit of Mars might have contained dozens of large bodies at one time. Each one had the potential to grow into a planet. But when two embryos collided, they became one. When an embryo passed close to Jupiter's powerful gravity, it might be scattered outward into the asteroid belt or flung completely out of the solar system. When smaller fragments drifted too close to the sun, they spiraled inward and disappeared forever. Over tens of millions of years, the crowded population thinned. The process resembles a slow gravitational tournament. Each round eliminates participants until only a few remain. By the time the giant impact phase ended, the inner solar system had settled into the four-planet arrangement we see today. That arrangement appears simple now, but it carries the imprint of all the earlier chaos. Take Mercury. Mercury's density is unusually high for a planet of its size. A large fraction of the planet is composed of metallic iron, far more than in Earth or Venus. One explanation suggests that Mercury once possessed a thicker rocky mantle similar to the other planets. During the violent early era, a massive impact may have stripped away much of that outer rock, leaving behind the metal-rich core and a thinner mantle. If so, Mercury is literally the surviving centre of a larger world that no longer exists. Mars offers another glimpse into what might have been. Mars appears to be a planetary embryo that never completed its growth. The region where Mars formed likely lost much of its building material early on, possibly because Jupiter's migration stirred and removed debris from that part of the disk. Without enough surrounding material, Mars simply ran out of resources. Its growth stalled. The planet we see today is essentially a frozen snapshot of an unfinished stage in planetary construction. Venus and Earth represent the two largest survivors of the process. Both worlds gathered enough mass to dominate their orbital neighbourhoods. Their gravity allowed them to accumulate thick atmospheres and maintain active interiors for billions of years. Yet even between these two near twins, subtle differences led to dramatically different outcomes. That pattern repeats throughout planetary science. Tiny variations during formation can amplify over time. A slightly different orbital distance changes how much sunlight reaches a planet. A slightly different rotation rate affects atmospheric circulation. A slightly different impact history alters the distribution of water or volatile elements. Over billions of years, those small differences compound until worlds that began similarly evolve into entirely different environments. Still, the foundation of their existence remains the same. Every rocky planet began as dust, microscopic grains drifting inside the solar nebula. To appreciate that transformation fully, it helps to pause and imagine the scale of it. Consider a single grain of mineral dust inside the early disk, a speck perhaps smaller than a grain of sand. That grain drifts through space, colliding gently with others, gradually becoming part of a pebble. That pebble becomes embedded in a larger clump. The clump merges with a boulder-sized aggregate. The boulder eventually becomes part of a kilometre-wide planetesimal. That planetesimal collides with other bodies, forming a planetary embryo hundreds or thousands of kilometres across. And after many more collisions, the material finally becomes part of a planet the size of Earth. The transformation spans more than 15 orders of magnitude in size, from microscopic dust to a world 12,700 kilometres across. Few processes in nature involve such an enormous range of scale. Yet gravity makes it possible. Gravity does not care whether it is pulling dust grains together or holding entire planets in orbit. The same force operates at every level of the process. Over time, gravity gathers scattered material into increasingly larger structures. Stars, planets, moons, even galaxies follow similar patterns. In the case of our solar system, gravity sculpted the protoplanetary disk into a structure with distinct zones. Close to the Sun, high temperatures allowed only rock and metal to survive. That region produced the rocky planets. Farther out, ice and gas accumulated into giant planets. Between Mars and Jupiter, the asteroid belt remained as a population of leftover fragments that never coalesced into a planet. And beyond the giant planets, the outer reaches of the solar system still contain enormous reservoirs of icy bodies, the Kuiper belt and the distant Oort cloud. All of these structures trace back to the same rotating disk of material. Even today, more than 4.5 billion years later, the solar system still carries the imprint of that early architecture. Planetary orbits remain aligned in roughly the same plane as the original disk. Most planets move in the same direction around the Sun. The spacing between worlds reflects the gravitational dynamics that emerged during the giant impact phase. When astronomers look at young stars across the galaxy and see disks of gas and dust surrounding them, they are witnessing the earliest stage of this same process. Some of those disks are only a few 100,000 years old. Others already show signs that planets are forming within them. Dark gaps appear where growing planets have begun clearing paths through the disk. Spiral patterns form where gravity reshapes the surrounding material. In those distant systems, the story we have been describing is happening right now. Dust is clumping. Pebbles are drifting together. Planetesimals are beginning to form. Some of those systems will eventually produce rocky planets. Some may build gas giants. Others might end up with architectures very different from our own. But the fundamental physics remains the same. Gravity gathering matter, collisions reshaping worlds, time allowing chaos to settle into order. And that realization leads to a subtle shift in perspective. For most of human history, Earth felt like a fixed stage where the drama of life unfolds. But planetary science reveals something deeper. The stage itself is the product of an ancient process. The continents, oceans, and mountains we see today are not permanent structures. They are the latest arrangement of material that has been evolving since the earliest days of the solar system. Even the ground beneath us is part of a story that began long before Earth existed. A story that started in darkness inside a cold cloud of drifting gas and dust. And from that quiet beginning, gravity slowly began assembling worlds. If we could travel back far enough in time, before the oceans, before continents, before even the first solid crust, Earth would not look like a planet ready for life. It would look unfinished. The surface would glow faintly in the darkness, its oceans not made of water but of molten rock slowly circulating under a heavy sky. Volcanoes would tower across the landscape, venting gases that thickened the early atmosphere. Above, the moon would appear enormous, hanging close and bright in the sky because its orbit had not yet expanded to the distance we see today. And occasionally the calm would break. A wandering asteroid or leftover planetesimal would streak across the sky and slam into the young world with tremendous force. For a brief moment, the surface would flash brighter as rock melted and debris blasted outward before falling back again. This was the final stage of planetary construction. Even after the main giant impacts had shaped the 4 rocky planets, smaller remnants of the early solar system still wandered through their orbits. Over time, those remnants steadily disappeared, either striking planets, falling into the sun, or being flung outward by gravitational encounters. The solar system was slowly cleaning itself up. But while that process unfolded, the planets themselves were undergoing internal changes that would determine their long-term futures. Heat played a central role. Much of that heat came from the violence of formation itself. Every collision during the giant impact phase delivered energy to the growing planets. When massive bodies merged, the kinetic energy of the impact converted into heat, melting large portions of the interior. Gravity added more. As a planet grew larger, its own weight compressed the interior rock, raising temperatures deep within the mantle and core. And there was another subtle heat source hidden inside the rocks. Many minerals contained radioactive elements such as uranium, thorium, and potassium. These elements decay slowly over time, releasing energy as heat. In the early solar system, radioactive isotopes were more abundant than they are today. Their decay helped keep young planets warm from the inside for hundreds of millions of years. The combined effect of these heat sources ensured that the interiors of rocky planets remained active long after their surfaces cooled. Inside Earth, heat rising from the deep mantle continues to drive slow convection currents, vast circulations of rock moving over millions of years. These currents push and pull on the planet's outer shell, breaking it into enormous plates that drift slowly across the surface. Where plates separate, molten rock rises from below and creates new crust. Where they collide, one plate may sink beneath another, carrying surface material back into the mantle. This process, plate tectonics, recycles Earth's surface continuously. Mountains rise, ocean basins open and close, continents drift. Over hundreds of millions of years, the entire face of the planet changes. That constant reshaping is unusual. Among the rocky planets, Earth appears to be the only one where plate tectonics operates in this global, long-lasting way. Mars shows signs that its surface moved in the distant past, but its smaller size allowed the planet to cool faster. The interior lost much of its heat, and the large-scale movement of crust eventually slowed and stopped. Mercury's crust contracted as the planet cooled, creating long cliffs where the surface buckled inward. Venus may still experience volcanic activity, but its thick, rigid crust does not appear to break into drifting plates the way Earth's does. These differences matter enormously for planetary evolution. On Earth, plate tectonics helps regulate the long-term climate. Carbon dioxide from volcanic eruptions dissolves into rainwater and reacts with rocks, eventually becoming locked inside minerals that are carried into the mantle by sinking tectonic plates. Later, volcanic activity releases some of that carbon dioxide back into the atmosphere. This slow cycle acts as a planetary thermostat, helping stabilize temperatures over geological timescales. Without such feedback mechanisms, climates can drift toward extremes. Venus likely experienced a runaway greenhouse effect in part because carbon dioxide accumulated in the atmosphere without a process to remove it efficiently. Mars, by contrast, lost much of its atmosphere and internal activity too quickly, leaving the surface exposed and cold. Earth sits in a narrow middle ground where geological and atmospheric processes interact in ways that maintain long-term stability. But none of that balance would exist if the earlier stages of planetary formation had unfolded differently. The Moon, for example, still plays a quiet but important role in Earth's story. Because the Moon formed from debris produced during a giant impact, it began its life orbiting very close to Earth, perhaps only 20 or 30,000 kilometers away. At that distance, tidal forces between the two worlds were immense. The Moon's gravity pulled strongly on Earth's molten oceans of rock, and later on its oceans of water. These tidal interactions gradually transferred energy between the two bodies. Over billions of years, the Moon slowly moved farther away while Earth's rotation slowed. In the distant past, a day on Earth may have lasted only 5 or 6 hours. Today it lasts 24. The Moon continues drifting outward even now, increasing its distance by a few centimeters each year. More importantly, the Moon helps stabilize Earth's axial tilt. Planets rotate on axes that are often tilted relative to their orbital planes. Earth's axis leans about 23 degrees, giving rise to the seasons. Without the gravitational influence of the Moon, that tilt might vary chaotically over time, producing extreme swings in climate. The presence of a large moon appears to help keep Earth's tilt relatively stable. Once again, the consequences of the early planetary collisions echo through billions of years of planetary history. The Moon itself is a reminder of the violence that shaped the inner solar system. Look at its surface through a telescope and you will see the record preserved almost perfectly. The bright highlands are covered with countless craters formed by ancient impacts. Dark plains known as Maria Mark regions where enormous collisions once fractured the crust, allowing lava to flood across the surface. Some of those basins span more than 1,000 kilometers. Each one marks a collision with an object large enough to devastate an entire region of the Moon. Earth must have experienced many similar impacts during the same era, but our active geology has erased most of those scars. Instead, the evidence lies hidden within the structure of the planet itself. The iron core that powers our magnetic field, the mantle convection that drives plate tectonics, the volatile elements that form oceans and atmosphere, all of these features trace back to the processes that assembled Earth from earlier bodies. In that sense, the solar system is not just a collection of planets orbiting the Sun. It is a fossil record. Every crater on the Moon, every asteroid drifting through the belt, every meteorite that lands on Earth carries information about the era when worlds were still forming. By studying those remnants, scientists can reconstruct events that occurred billions of years ago. And the picture that emerges is both violent and strangely elegant. Dust drifting in a disk around a newborn star, pebbles gathering under the influence of gravity, planetesimals forming suddenly from collapsing swarms, embryos colliding again and again until only a few worlds remain. The rocky planets were not sculpted delicately into existence. They were assembled through collision, survival, and time. And even now, long after the chaos ended, the quiet orbits of Mercury, Venus, Earth, and Mars still reflect that ancient process. 4 survivors moving steadily around the Sun. 4 survivors? That is what the inner solar system eventually became. After tens of millions of years of collisions, mergers, and gravitational scattering, the chaos of planetary construction gradually gave way to a stable arrangement. Mercury, Venus, Earth, and Mars continued orbiting the Sun in roughly the same plane where the original disk once rotated. Everything else had either been absorbed, shattered, or expelled. But stability did not mean perfection. Each of the surviving planets carried the physical consequences of the process that built it. Mercury, the smallest and closest to the Sun, became a dense, metal-heavy world. Its iron core occupies an unusually large fraction of the planet's interior, giving Mercury a density almost as high as Earth's, despite being far smaller. The planet's surface tells the story of a world battered early and then frozen in time. Vast cratered plains stretch across its landscape, preserved because Mercury has little atmosphere and very little geological activity capable of erasing ancient scars. Temperatures on Mercury swing wildly. During the long Mercurian day, sunlight can heat the surface above 400 degrees Celsius. During the equally long night, the temperature plunges hundreds of degrees below freezing. It is a harsh place, and yet even Mercury reveals clues about the solar system's birth. The composition of its rocks and its oversized metallic core hint at collisions that stripped away outer layers long ago. Move outward and the next world is Venus. In many ways, Venus is Earth's closest sibling. Its diameter is only slightly smaller than our planet's, and its bulk composition appears similar, rocky mantle surrounding a metallic core. But the surface of Venus today could hardly be more different. A dense atmosphere made almost entirely of carbon dioxide presses down on the planet, with a pressure 90 times greater than Earth's sea level atmosphere. Thick clouds of sulfuric acid swirl high above the surface, reflecting sunlight and hiding the terrain below. Beneath those clouds lies a world hotter than any other planet in the solar system. Surface temperatures exceed 460 degrees Celsius. Lead would melt there. The reason lies in the greenhouse effect. Carbon dioxide traps heat efficiently, preventing infrared radiation from escaping back into space. Over time, that heat accumulates, raising the planet's temperature higher and higher. On Earth, carbon dioxide is balanced by oceans and geological processes that remove it from the atmosphere over long time scales. On Venus, those balancing mechanisms appear to have failed or never fully developed. The result is a planet locked into extreme heat. And yet, beneath the clouds and the oppressive atmosphere lies a surface shaped by the same early events that formed the other rocky worlds. Venus once experienced magma oceans, volcanic outgassing, and countless impacts during the era of planetary formation. Its present condition is the outcome of how those early conditions evolved. Next comes Earth. Among the 4 rocky planets, Earth occupies a remarkably balanced position. Its distance from the Sun allows liquid water to remain stable on the surface. Its size provides enough gravity to hold an atmosphere while also retaining internal heat. Its magnetic field protects the atmosphere from solar wind erosion. Its oceans interact with the atmosphere and crust in ways that help regulate climate. But Earth's early history was no less violent than that of its neighbours. The giant impact that formed the Moon reshaped the planet completely. Large regions of the mantle melted. Debris filled orbit around the planet. The surface cooled again only after enormous amounts of heat radiated into space. Over time, oceans formed. Plate tectonics began recycling crust. Chemical cycles stabilized the atmosphere. Life emerged. And life itself eventually became one of the most powerful forces shaping the planet's surface and atmosphere. Finally, there is Mars. At first glance, Mars appears similar to Earth in many ways. It has polar ice caps, enormous volcanoes, valleys carved by ancient water, and landscapes shaped by wind and dust storms. But Mars is smaller, only about half Earth's diameter and roughly 1/10 its mass. That difference had enormous consequences. Because Mars is small, it lost internal heat more rapidly than Earth. Its magnetic field faded early in the planet's history, leaving the atmosphere exposed to the solar wind. Over time, the atmosphere thinned dramatically. Without thick air and strong greenhouse warming, surface temperatures dropped. Water that once flowed across the landscape either froze underground or escaped into space. Mars became a cold desert world. Yet the planet still preserves evidence that it was once warmer and wetter billions of years ago. River channels snake across its ancient terrain. Sedimentary rocks record the presence of long-standing lakes. Mars represents a planet that began forming like Earth, but followed a different path once its size limited its ability to retain heat and atmosphere. Taken together, these 4 worlds show how the same basic formation process can lead to very different outcomes. All 4 began in the same disk of dust and gas. All 4 grew through the same stages of planetesimals and embryos. All 4 endured the violent giant impact phase. And yet their later histories diverged dramatically. Mercury became dense and airless. Venus became a furnace. Earth became a living world. Mars became a frozen desert. The differences emerged gradually, shaped by small variations in mass, distance from the Sun, internal heat, atmospheric chemistry, and impact history. But beneath those differences lies a deeper unity. Every atom in the crust of these planets was once part of the solar nebula. The iron in Earth's core was forged inside ancient stars that lived and died long before the Sun existed. The silicon in rocks once drifted as microscopic dust grains inside the protoplanetary disk. Even the water in Earth's oceans may have arrived partly through collisions with icy bodies that formed farther from the Sun. In that sense, planets are not just objects orbiting a star. They are the final arrangements of material that has travelled through many stages of cosmic history, from stellar explosions, to interstellar clouds, to protoplanetary disks, to planetesimals and embryos, to the finished worlds we see today. And when we observe other stars surrounded by dusty disks, young systems where planets are just beginning to form, we are witnessing earlier chapters of that same story. Around those distant stars, dust grains are already colliding and sticking together. Pebbles are gathering into larger clusters. Planetesimals are beginning to emerge. Some of those systems may one day host rocky planets, perhaps worlds with mountains, oceans, or atmospheres of their own. Perhaps worlds where life could eventually appear. The processes unfolding there are the same ones that shaped the inner solar system billions of years ago. Gravity gathering matter, collisions reshaping worlds, time slowly turning chaos into structure. And from that long process emerged the quiet arrangement of planets we see tonight when we look up at the sky. 4 rocky survivors orbiting a star that formed from a cloud of dust. When we look at the inner solar system today, it is easy to believe the arrangement is permanent. Mercury circles the Sun every 88 days. Venus follows a little farther out. Earth completes its familiar yearly orbit while Mars drifts slowly beyond. Their paths appear steady and reliable, repeating with such precision that we can predict their positions centuries in advance. But that calm rhythm hides a truth that stretches far back in time. These orbits were not guaranteed. They are the result of billions of years of gravitational negotiation. In the earliest era, the region around the Sun was crowded with far more worlds than exist today. Dozens of planetary embryos once travelled through the inner solar system, each tugging on the others, each competing for space and material. The orbits we see now are simply the few that remained stable after all the others were removed. Over long spans of time, gravity naturally favours arrangements where bodies keep a safe distance from one another. If 2 planets drift too close or cross paths repeatedly, their interactions eventually lead to instability. One may collide with the other. One may be scattered into a distant orbit. One may even be thrown out of the solar system entirely. The survivors are the ones that end up spaced in ways that minimize these dangerous encounters. This gradual sorting process is why the inner planets appear separated by such clear gaps. Mercury's orbit lies well inside that of Venus. Venus and Earth are separated by tens of millions of kilometers. Mars orbits still farther out. Those distances reflect a kind of gravitational spacing that allows the system to remain stable over enormous periods of time. Yet even now, the solar system is not perfectly static. The gravitational pull between planets slowly alters their orbital shapes. Over hundreds of thousands or millions of years, the orbits stretch slightly, tilt slightly, and precess like spinning tops. These variations are small enough that the system remains stable, but they remind us that motion and change are still happening. In fact, the solar system behaves more like a slow conversation between massive bodies than a fixed mechanical clock. Each planet subtly influences the others. Jupiter, despite orbiting far beyond Mars, still exerts a gentle pull on the inner planets. Its enormous mass, more than twice that of all the other planets combined, makes it the dominant gravitational presence after the Sun itself. Over long timescales, Jupiter's gravity can slightly shift the eccentricity of Mars's orbit, or alter the tilt of Earth's orbit. Those effects are small, but they accumulate slowly over millions of years. Planetary systems everywhere behave this way. Gravity weaves together the motions of every object, creating patterns that evolve gradually but continuously. Yet the remarkable fact about our solar system is how long its current arrangement has endured. For more than 4 billion years, the 4 rocky planets have circled the Sun without catastrophic disruption. Impacts still occur occasionally, but they are now rare events rather than routine parts of planetary growth. That stability gave Earth something extraordinary. Time for oceans to persist. Time for chemical evolution to unfold. Time for life to arise and gradually diversify across the planet's surface. If the inner solar system had remained chaotic, if giant impacts continued frequently, or if planetary orbits were unstable, such long-term development might never have been possible. In that sense, the calm architecture we see today is not just an astronomical detail. It is the quiet foundation that allowed the biological history of Earth to unfold. But step back even farther and the perspective becomes even larger. The formation of rocky planets around stars appears to be common throughout the galaxy. Astronomers now know that most stars are surrounded by planets. Some systems contain giant worlds far larger than Jupiter. Others host compact families of rocky planets packed much closer to their star than Mercury is to the Sun. Still others may contain planets wandering through space alone, having been ejected from their original systems during violent gravitational encounters. The diversity is enormous, yet despite that variety, the basic process remains consistent. Stars form from collapsing clouds of gas and dust. Rotating disks appear around those young stars. Inside the disks, microscopic particles begin sticking together. Pebbles form. Planetesimals appear. Embryos collide and merge. Planets emerge. In that sense, the story of the inner solar system is not unique. It is one chapter in a cosmic pattern repeated across the Milky Way, billions of times. And when we observe distant protoplanetary disks, glowing rings of dust surrounding newborn stars, we are looking at environments that resemble the solar system during its earliest days. Some of those disks already show gaps where growing planets have begun clearing their paths. In others, spiral waves ripple through the dust as gravity shapes the disk. Inside those distant systems, the same quiet processes are unfolding. Dust drifting through space. Pebbles gathering. Small worlds forming from the slow pull of gravity. Some of those systems will eventually produce rocky planets orbiting in stable zones around their stars. On a few of them, perhaps, conditions will allow liquid water to exist on the surface. And on an even smaller number, chemistry might take the next step and produce living systems. We cannot yet see those distant surfaces directly, but we know the physics that builds them. Because that physics built our world. The mountains beneath our feet, the iron core deep inside Earth, the moon rising each night above the horizon, all of it traces back to that ancient disk of gas and dust surrounding a young sun. For millions of years, gravity shaped that disk into ever larger structures. The smallest particles gathered into pebbles. Pebbles collapsed into planetesimals. Planetesimals collided to form embryos. Embryos merged through enormous impacts. And from that chaotic process, the 4 rocky planets of the inner solar system emerged. Their surfaces cooled. Their interiors differentiated. Their atmospheres evolved. Over time, each world followed its own path. Mercury hardened into a metal-rich relic close to the Sun. Venus became wrapped in a crushing greenhouse atmosphere. Mars cooled into a cold desert, preserving ancient scars. And Earth, by a combination of size, distance, chemistry, and history, became a place where oceans and life could exist. But beneath all those later differences, their origin remains shared. They were assembled piece by piece from the same swirling cloud of dust that once surrounded the newborn sun. If we compress the entire history of the inner solar system into a single long moment, its story becomes easier to feel. At the beginning, there is only a cloud. Cold gas drifting between the stars, carrying atoms forged in older suns. For millions of years, nothing dramatic happens. The cloud remains dark and quiet. Then gravity slowly begins to gather the material. The cloud collapses. A young star ignites at the center. Around it spreads a rotating disk of gas and dust stretching billions of kilometers into space. Inside that disk, the first solids appear. Tiny grains of mineral dust condense out of the hot gas. They drift gently through the disk, colliding with one another, sticking together through delicate electrostatic forces. Nothing about this stage looks impressive. Each particle is microscopic. Yet this is the beginning of every rocky world that will ever exist in the system. Slowly the grains gather. Clusters form. Pebbles emerge. Over thousands of years, the disk fills with countless drifting particles, each one slightly larger than before. Then gravity begins to take hold. Streams of pebbles concentrate into dense clouds. Those clouds collapse into the first planetesimals, rocky bodies kilometers wide, the size of mountains drifting through space. Now the process accelerates. Planetesimals collide, merge, and grow. Their gravity sweeps up nearby debris. A few fortunate bodies become larger than the rest. Planetary embryos appear, These embryos are unfinished worlds, some already the size of our moon or even Mars. Dozens of them circle the young sun, pulling on one another's orbits in an intricate gravitational dance. For a time, the inner solar system becomes crowded with these embryonic planets. But crowded systems cannot remain stable forever. Their orbits gradually shift. Close encounters alter trajectories. Sooner or later, worlds collide. And when worlds collide, everything changes. Rock melts. Fragments scatter. Entire bodies merge together to create larger planets. This stage, the giant impact phase, lasts tens of millions of years. It is the most violent chapter in the birth of the rocky planets. Some embryos are destroyed. Others grow. A few become dominant, sweeping up material from their surroundings while scattering smaller bodies into distant orbits. Eventually, the number of worlds declines. 20 become 10. 10 become 6. 6 become 4. Mercury. Venus. Earth. Mars. The survivors settle into stable orbits around the Sun. But even then the story's not finished. The surfaces of these young planets remain molten for long periods. Oceans of magma cover their landscapes while heavy metals sink toward their centers, forming dense iron cores. Volcanoes release gases that build the first atmospheres. Asteroids and comets continue striking the planets, delivering additional material from the outer solar system. Gradually the heat escapes into space. Crusts solidify. Oceans appear on Earth. Mars cools and grows quiet. Venus develops its crushing atmosphere. Mercury's surface hardens beneath the intense sunlight. The solar system calms. The chaotic construction site becomes a stable planetary system. For billions of years afterward, the 4 rocky worlds continue circling the Sun, their early violence preserved only in craters, meteorites, and the hidden structures of their interiors. And yet the deeper truth remains. The ground beneath us was once part of that chaos. Every mountain on Earth is built from rock that formed in ancient collisions. The iron in Earth's core sank downward while the planet was still molten. The Moon itself was born from debris blasted into orbit during one of the last great impacts. Our world is not separate from the solar system's turbulent past. It is the result of it. When we stand on solid ground today, it feels permanent and quiet. Continents drift slowly. Mountains rise and erode, oceans move with the tides. But those gentle processes are only the latest chapter of a far longer story. A story that began with dust. Dust drifting through a disk around a newborn star. And from that dust, through gravity, collision, heat, and time, entire worlds were assembled. The 4 rocky planets we see today are simply the final shapes that remained when the storm of planetary formation finally settled. They are the survivors of the solar system's earliest age. Yet even after everything we have traced, the dust, the pebbles, the embryos, the collisions, the most remarkable part of the story may be how quiet the result eventually became. Planetary formation is loud in its physics but slow in its tempo. It unfolds across tens of millions of years, with long stretches of calm punctuated by rare but transformative events. When we compress that timescale into human imagination, it can feel like a sequence of explosions and catastrophes. In reality, most of the time the early solar system simply waited. Worlds orbited. Gravity tugged gently. Orbits drifted little by little until eventually 2 bodies crossed paths. Then, briefly, something immense happened. Rock vaporized. Debris spread into space. Gravity gathered it again. And then the waiting resumed. That rhythm, long patience interrupted by decisive events, is what allowed the inner solar system to evolve from a cloud of dust into a small family of planets. And once the major collisions ended, the rhythm changed again. The solar system became quieter. Asteroids still moved through space, but far fewer remained. Impacts still occurred, but they became rare compared with the earlier era. The 4 rocky planets settled into their gravitational balance, each occupying a stable region of orbit around the Sun. Over time, their surfaces cooled and hardened. Their atmospheres changed. Their interiors slowly lost heat. Billions of years passed. On Mercury, the crust contracted as the planet cooled, leaving enormous cliffs that still cut across the landscape today. These scarps stretch for hundreds of kilometers, marking places where the shrinking planet wrinkled its own surface. On Venus, volcanic plains spread across vast regions of the planet. Lava flows buried older terrain beneath newer layers, reshaping the surface again and again beneath the thick clouds. Mars preserved some of the solar system's largest volcanoes, including Olympus Mons, a mountain so immense that it rises nearly 3 times higher than Mount Everest. And on Earth, the restless motion of tectonic plates continually recycled the crust, erasing many of the earlier scars of formation. The continents we see today did not exist during the first billion years of Earth's history. They formed gradually through volcanic activity, collisions between crustal fragments, and the slow rise of buoyant rock from the mantle below. Even now, the continents continue to move. If you could watch the Earth from far above for millions of years, you would see the land slowly rearranging itself. Oceans widening, mountains rising and eroding, entire landscapes appearing and disappearing. All of that motion traces back to heat trapped inside the planet since its formation. The energy delivered by ancient collisions, the compression of gravity, and the decay of radioactive elements still shape Earth's internal dynamics today. The consequences reach all the way to the surface. Volcanoes release gases that replenish the atmosphere. Plate tectonics cycles carbon between rocks and air, helping stabilize the climate. The magnetic field generated by the churning iron core protects the planet from solar radiation. These features are not separate from the story of planetary formation. They are its continuation. What began as dust and gravity eventually became a living system of geological cycles. And that realization brings the story back to something very close to us. When you pick up a rock from the ground, you are holding material that has traveled through extraordinary stages of cosmic history. The atoms inside it may have formed in ancient stars that exploded billions of years before the sun existed. Later, those atoms drifted through interstellar clouds until gravity gathered them into the solar nebula. Inside that disk, they became dust grains. Those grains stuck together to form pebbles. Pebbles joined planetesimals. Planetesimals collided inside growing worlds. Eventually, that material became part of the planet we now call Earth. The rock you hold is the latest form of matter that has been reshaped again and again across cosmic time. Even the air we breathe carries that history. The nitrogen and oxygen molecules in the atmosphere were once locked inside minerals within the early planet. Volcanic eruptions released them. Chemical reactions altered them. Life itself changed their balance. The water in Earth's oceans contains hydrogen that formed shortly after the Big Bang, and oxygen that formed inside ancient stars. The solar system is not just a collection of objects. It is a long chain of transformations. Gas to dust, dust to rock to planet, planet to world, and in at least one place, on this small rocky world orbiting an ordinary star, that chain continued one step further. Matter became aware of itself. From the perspective of the cosmos, that step may be rare. It required a stable planet with liquid water, a protective atmosphere, long periods of relative calm, and the slow unfolding of biological evolution over billions of years. But none of it could have happened without the earlier steps, without the dust drifting inside the solar nebula, without the planetesimals colliding and merging, without the giant impacts that assembled the rocky planets. The quiet stability of the inner solar system today rests on the foundation of that ancient chaos. 4 rocky worlds orbiting a star may seem simple when viewed from a distance. Yet each of those worlds carries the memory of an extraordinary beginning, a beginning where dust learned how to become planets. Now, after billions of years of motion, the inner solar system appears calm enough that we sometimes forget how improbable its history truly is. Mercury continues its tight orbit close to the Sun, completing a full circuit in less than 3 Earth months. Venus glows brightly in our skies, wrapped in its thick clouds. Earth follows its steady path through the habitable zone, oceans reflecting sunlight back into space. And Mars drifts along the outer edge of the rocky region, quiet and cold. 4 planets, 4 stable paths, but that simplicity is the final outcome of a story that could easily have ended very differently. If Jupiter had migrated a little farther inward during the early days of the solar system, its gravity might have swept away much of the material that formed Earth and Venus. The inner disk could have been stripped nearly clean, leaving perhaps only a few small rocky remnants orbiting close to the Sun. If one of the giant impacts during the embryo phase had struck Earth at a slightly different angle or speed, the resulting world might have spun differently, cooled differently, or lost much more of its outer layers. If Mars had formed in a region with more available material, it might have grown into a second Earth-sized world rather than remaining a small planetary embryo frozen in time. The solar system we inhabit is only one of many possible outcomes, and that realization grows stronger every time astronomers discover new planetary systems around distant stars. Some stars host giant planets skimming close to their surfaces, completing an orbit in only a few days. Others contain chains of rocky worlds packed tightly together, each circling the star faster than Mercury orbits the Sun. There are systems where planets follow elongated, chaotic paths that bring them swinging inward and outward across huge distances. There are even stars with planets that appear to have migrated wildly through their systems before settling into new positions. Compared to many of these discoveries, our solar system appears unusually orderly. The rocky planets remain close to the Sun. The gas giants occupy distant orbits. The asteroid belt sits between Mars and Jupiter as a leftover relic of the formation era. That structure may not be the most common arrangement in the galaxy, but it is the arrangement that allowed Earth to exist. It allowed a rocky planet to form in a region where temperatures permitted liquid water. It allowed billions of years of orbital stability. It allowed time, and time is perhaps the most important ingredient in the entire story. Because while planets can form in tens of millions of years, the processes that transform a world, cooling, atmospheric evolution, biological development, unfold across billions. The inner solar system has been stable long enough for those slower processes to take place. The continents have moved. Mountains have risen and eroded. Oceans have circulated around the planet countless times. Life has evolved from microscopic cells into forests, reefs, animals, and eventually conscious beings capable of asking how the planets themselves were born. That last step may be the most astonishing consequence of the entire process. The atoms that once drifted through the solar nebula are now part of minds capable of reconstructing their own origins. Human beings did not witness the formation of the solar system. Yet by studying meteorites, planetary surfaces, distant protoplanetary disks, and the physics of gravity and chemistry, we can piece together the sequence of events that occurred billions of years before our species existed. We can trace the path from dust to planets, and when we do, something quietly profound happens to our sense of the familiar world around us. The ground beneath your feet is no longer just ordinary rock. It is the end result of ancient collisions between planetary embryos. The iron inside Earth's core is metal that once sank through oceans of molten rock early in the planet's history. The moon rising above the horizon is the frozen remnant of debris blasted into orbit during a giant impact that reshaped the young Earth. Even the asteroids drifting quietly between Mars and Jupiter are survivors of that distant era, when the solar system was still assembling itself. Everything we see in the inner solar system today is a fossil of that process, a record written in rock, orbit, and gravity. And the story does not truly end here, because the same physics continues operating elsewhere in the galaxy. Around young stars right now, new disks of dust are forming. Inside those disks, particles are sticking together. Pebbles are gathering. Planetesimals are appearing. Embryos are beginning their slow gravitational dance. Millions of years from now, some of those systems will contain rocky planets circling their stars, worlds with mountains and atmospheres of their own, worlds that began exactly the same way ours did, as dust. If we could step far outside the solar system and watch its earliest moments unfold again, the process might seem almost impossibly slow. Tiny particles drifting through darkness, gravity pulling gently but persistently, collisions occurring rarely but decisively. Yet over millions of years, that quiet persistence would build something extraordinary. From dust, entire worlds would emerge. And one of those worlds, after billions more years of cooling, change, and evolution, would become the place where you are standing now, a survivor of the solar system's violent birth, a fragment of ancient collisions, a small rocky planet assembled piece by piece around a young star. The ground beneath your feet is not merely stable ground. It is the final shape taken by dust that learned, through gravity and time, how to become a world.